All right, here we go. This is going to be a good old conservation of energy question. We've got a 2.5 kilogram ball, which is held 3 meters above a spring. So ball, 3 meters, positioned onto the ground. There we go. The ball is dropped onto the spring, and the spring is going to compress 12 centimeters, so 0.12 meters in bringing the ball to rest. And the question is, what is the spring constant? All right, now the easiest way to do this, there's a lot of ways to do this, but the easiest way to do this is to consider the ball, spring, earth system. Now, if we do that, then the elastic potential energy will be internal to our system, and the gravitational potential energy will be internal to the system. Now, it's actually really tempting in this situation to do the ball down to the point right before it hits the spring, and then do the point from where it hits the spring until the spring is compressed. And it's very, very tempting to do that, to break this into 2 pieces. But you don't have to, because the only forces that are here are gravity and the force of the spring. And so what we're going to do is we're just going to set it up. We're going to say that the work is equal to the change in the kinetic energy plus the change in the gravitational potential energy plus the change in the elastic potential energy, just like that. All right, now, as we mentioned, there are no other forces here, right? We ignore air resistance like normal, and the only other forces are the spring and gravity. And so because of that, we can actually say that no work is being done. All right, now we're going to do the kinetic energy final minus the kinetic energy initial. There are other ways to do this, but I find that this is the surefire way of making sure that we don't make any mistakes as we go through. And so I'm doing the final minus initial for each of those terms, and then we're going to look at in each of those terms which ones we can cross out. Now we'll notice that the ball is being held and then dropped. That means that my initial kinetic energy is 0, and then at the end it does say that we're bringing the ball to rest, which means my final kinetic energy is 0 as well. And you may be concerned about the changes in between. Don't be, because that energy is always present. The energy is either kinetic, or it's gravitational potential, or it's elastic potential, and it can convert back and forth. Because there are no other forces, we don't have to worry about anything else. Okay? The gravitational potential energy final, I'm going to go ahead and define this as position 0, which means that gravitational potential final is going to be 0. Now I am going to have some initial gravitational potential energy because I start 3.12 meters above where it eventually stops. Okay? Then we've got our elastic potential energy, which initially, that one is also 0 because there's no compression of the spring initially. So essentially what that means is that we've gotten down to this situation where all we have is the negative gravitational potential energy initial plus the elastic potential energy final, and those will equal 0, or essentially they're going to be equal to each other. And so I'm going to go ahead and add this guy to the other side, and I'm going to put in the MGH for that. It's going to be positive now. Needs to equal the 1/2 kx squared. Now, in a way, this should make sense, because however much energy I started with, all that gravitational potential energy needs to end up being elastic potential energy. All that energy gets stored as long as there's no external forces causing me to lose energy. So at this point, we should be able to throw in numbers. We got the mass. Now the mass here, you notice that sometimes we were able to cancel the mass out when we were using kinetic energy and gravitational potential energy, but this elastic potential doesn't depend on the mass of the object. It depends on how much energy is stored inside the spring. And so we're actually not going to be able to cross out mass this time. We'll have the 2.5, we'll have the 9.8, and then we'll have that height, which was 3.12. Okay? Notice that it was 3 meters above the spring. When it hits the spring compresses for another 12 centimeters. So that would give us that total of 3.12. This is going to be equal to 1/2 times k, which is what it's asking for, times that x, which is the compression, which is 0.12. And so at this point, I should be able to solve for k. Now when I do this, and I'll let you do the algebra, I end up getting that K equals 130.876, right? It just kind of goes on. Because I'm looking at my data up above, everything's in 2 sig figs, I'll go ahead and write my final answer that K equals 130 newtons per meter, which is the units of that spring constant there. So there we go. We found the spring constant. We were able to do that using conservation of energy. All right, let's go check out another example.